All right, let's jump right in. Today, we're going on a bit of an archaeological dig. We're going to uncover this hidden thread that connects the golden age of 16-bit gaming directly to the most powerful supercomputers we have today. It's a wild story.
So, our story starts with these old design documents, a kind of guidebook for a 1995 Amiga game called Alien Bash. But look, this isn't some dusty history lesson. As the quote says, this is about the archaeology of working code that performed miracles under some absolutely insane limitations.
And that right there, that's the central mystery we're tackling. Because when people started digging through these old notes, they found something that just shouldn't be possible. The rules and the patterns laid out for this ancient game, running on an old Motorola 68K chip, look almost identical to the rulebook for programming modern NVIDIA GPUs. So how on earth can that be? Well, let's find out.
First, you got to picture the world of 1995. Programming for the Amiga 68K was a constant battle. You had maybe 2 megabytes of RAM to play with and a processor that's like a fraction of the speed of the chip in your watch. To get swarms of aliens flying around on screen, you couldn't just write code. No, you had to carve it directly into the silicon.
And when you're under that much pressure, you don't just find clever tricks. You discover fundamental truths. And that's what happened here. A set of super efficient patterns emerged that the guidebook calls the 6 primitives. These weren't just trends, you know? They were timeless solutions forced into existence by the physical limits of the hardware itself. So let's start decoding these primitives. We're going to kick things off with one of the most important ones, a pattern that deals with the most precious, the most scarce resource back then, computer memory.
Meet primitive number 5, the pool. And the idea here is it's brilliantly simple. Instead of creating a new alien every single time one pops up on screen and then deleting it when it gets shot, the game does something way smarter. It creates every single alien it will ever need right at the very beginning. It pre-allocates this fixed-sized collection, a pool, and then it just recycles them.
And this is why it's so fast. You need a new alien? The game just scans its list of 100 slots, finds the first one that's turned off, and flips its little active switch to on. That's it. The whole thing takes microseconds. And crucially, it completely avoids asking the system for new memory in the middle of the action, which was a notoriously slow, unpredictable operation that would have totally destroyed the game's smooth frame rate.
Each one of those little objects in the pool was called a control block, or a CB, and you can think of it like a perfectly organized 50-byte atom of data that held everything about a single alien. The pool, then, was the field where all these atoms lived. And this super rigid structure made the whole system incredibly predictable. And in computing, predictable means fast, really, really fast.
Okay, but these patterns, they're just one part of the story. The guidebook also uncovers something way deeper, unbreakable laws of physics that control performance on any computer, whether it's from 1995 or from today.
This is law number 2. And honestly, if you take one thing away from this, it's this. The secret to high-speed code isn't really about how many gigahertz your processor has. It's about how you access memory. The way you step through your data, what they call your stride, that determines everything. It's your destiny.
And we're not talking about a small difference here. The original documents and modern tests have confirmed this. They show that doing it the right way versus the wrong way can lead to a 50-to-1 speed difference. 50 times faster just by changing the pattern of how you read your data. It's insane.
And this chart just lays it out perfectly. That scattered access on the left, where your code is jumping all over memory, that's like trying to read a book by picking one random word from each page. It's just painfully slow. But sequential access, reading one thing right after another, that's like reading a book line by line. The hardware can guess what you'll need next, and it just flies.
Which brings us right to law number 1. Math is cheap, but moving data is incredibly expensive. Look at this table. A couple of simple additions, that might take, say, 2 processor cycles. But just fetching the data from memory and writing it back, that can cost 600 cycles. That's a 300-to-1 ratio. The bottleneck is never the math. It's always the data transfer. And that right there is why your stride is destiny.
Okay, so we've got these ancient patterns and these unbreakable laws. So what? Well, here comes the big reveal. This isn't just history. These principles are the exact fundamental blueprint for how we write high-performance code for modern NVIDIA GPUs.
Let's look at the evidence. Exhibit A, time. The Amiga game used a hardware signal called the V-blank interrupt to lock its game loop to a perfect 50 frames per second. The frame was the contract. Fast forward to today.
In CUDA, the language for GPUs, there's a command called CUDA device synchronize. And what does it do? It creates a hard boundary, making sure all the parallel work is done before the next frame of computation begins. It's the exact same contract.
Now remember our pool primitive? Well, guess what? It is still the absolute gold standard in GPU programming. You never ask for new memory or malloc in a performance-critical loop, ever. Instead, you use a function like CUDA-malloc to pre-allocate everything you could possibly need right up front into a fixed pool. And why? For the exact same reason as 1995. It's predictable and it's fast.
And the final piece of the puzzle is the data structure itself. Remember that rigid 50-byte control block? Modern GPUs demand that same exact discipline. CUDA has these super strict rules about how your data has to be aligned in memory. And it's all to achieve something called memory coalescing, which is really just a fancy modern term for that perfect sequential, straight-line memory access we were just talking about. The goal hasn't changed one bit. So you see, this isn't some crazy coincidence. It's not like the engineers at NVIDIA were digging up old Amiga games. It's convergent evolution. It's two completely different systems, decades apart, being forced by the very same laws of physics, the same limits of silicon and memory latency, to arrive at the exact same solutions.
So what's the big lesson here? What's the takeaway from all this? It's that if you really want to build fast software on any platform, you have to understand these timeless rules. You have to understand the physics of the machine, not just the hot programming language of the day.
And check this out. This is the final mind-blowing piece of evidence. The game had 100 aliens in its pool. Why 100? It sounds totally arbitrary, right? Well, it turns out 100 was the perfect number to fit neatly inside the tiny 8-kilobyte cache of the 68K chip. But get this. Decades later, it was also a near-perfect number to spread across the cores of a PlayStation 3. And today, it's an optimal number for a modern NVIDIA GPU to process in what are called warps. It just works every time.
The point is, those numbers, those constants, they weren't arbitrary at all. They were what we call hardware-driven invariants. The creator of Alien Bash wasn't just making up numbers. They were uncovering these fundamental constants of high-speed computation that would hold true for decades to come. And that brings us to the ultimate lesson from this ancient guidebook. The fastest code doesn't try to bend the hardware to its will. It does the complete opposite. You reorganize your problem, you change your data, you rewrite the world itself to perfectly match the physical reality of the machine.
Which leaves us with one last question to chew on. What are the essential physics-driven patterns that we're using right now? You know, among all the different frameworks and languages we use today, which parts are just temporary trends? And which ones are the timeless laws that programmers in the year 2050 will be rediscovering all over again? Pretty interesting thing to think about. Thanks for tuning in.